Last kind of subject in 4.2 is exponential models. So here's where we take basically the A-PERT equation and we reuse it with that base E is very important, and it comes up in some practical applications talking about growth and decay, and you can always find, like, usually this is in radioactive material, it decreases at some amount, at some certain rate. We have radioactive decay, it decreases at some rate. So we can use this to find the ending amount after so many years, which would be time t. So this is very similar to A-PERT, where our k is our rate of decrease. T is same time in years. E is the E button on your calculator. And P and Y sub 0 the same kind of thing. The principle for the application problems and the growth and decay, it is the amount of the initial amount of whatever initial quantity. So it's the amount of material you're first dealing with, and then A and Y would be how much you're left with at the end of a certain amount of time. So we can use this to solve exponential growth and decay problems. And so let's go ahead and do an example. Okay, so this data here, you have your years and you have your carbon dioxide levels. So this is data from the past several years to indicate the future amounts of carbon dioxide in the atmosphere, and so we're estimating the carbon dioxide in the atmosphere, and these are parts per million. So these levels are in parts per million, and what we want to do is we want to use this model, y equals 0.001942 times E raised to the 0.00609 times X, and X is equal to the time in year. So that'd be like, for instance, excuse me, if I plugged in X equals 1990, then I would get 353. Okay, so we want to figure out, by using this model, can we figure out what the carbon dioxide levels will be in the year 2015. Okay, so then I just enter this into my calculator. I can enter it just like this, 0.001942. Press the E button. It should automatically pop up something like that, or a box. And then we can put our rate right here, and then times by our year, and our year is the actual year, so not 25. The difference between 1990 and 2015, it's the actual year 2015. Then push multiply by 2015, end your parenthesis, press enter or equals, and you will get 414.6. If we round to the nearest parts per million, it'd be 415 parts per million. Okay, so now you can go ahead and try on your own, try to do that same thing, use that same model, and go ahead and see when is the amount in the year 2000. So the amount at year 2000, what year will that be double? Okay, so what year will that amount double? Okay, so here you're finding X. Okay, you're finding that year. You're given the amount at the end. So this equals the amount at the end, right? So go ahead and pause the video and try that. Okay, if you are stuck, here is the estimate. We want it to double. So that's 750. We want our amount at the end to be 750. Here is our formula, 0.001942 e raised to, well, I'm not going to put that in my calculator, raised to 0.00609x, and now I'm solving for x, right? First thing we got to get rid of this multiplying by our initial amount here, which in this problem doesn't really mean our initial amount, but that's kind of the formula, right? The P, the principal, represents that initial amount. So I got to take 750 and divide that by 0.001942. Okay, and of course that number is going to be pretty big, and I probably want to keep that number in my calculator. I don't want to round it yet, so I just kind of hold on to it. Well, the decimal does end, but maybe it keeps on going. It's kind of hard to tell because all those numbers take up your calculator. 609 times x. Okay, so I need to get that x out of the exponent, right? Okay, and there can be a few ways to solve this. From here, kind of haven't quite learned it yet. We will learn it in the next section or so. But we could switch this to a log, which you know how to do that. So it could be log base e of 386,199.794 equals what my exponent is, right? 0.00609x. Right. Well, this button is in your calculator. It is the LN button. Okay, so that is the LN button. And you can type ln of 386,199.794 equals 0.00609. So I'm going to hold on, don't put that in your calculator yet, because then we can divide by 0.00609 on both sides, and then we have our x, right? Okay, so I have this number in my calculator still. It hasn't changed. I didn't delete it or anything because I don't want to round it yet. So how I can type ln of that button, I type the ln button, okay, which pops up a parenthesis, and then I can hit my answer button, whatever that might be. Sometimes it's a straight button, sometimes you have to hit second negative button. What I have to do, I'm going to end my parenthesis, and then I'm going to hit divided by, and I'm going to do 0.00609, and that will give me my answer. Which is 2,112.33, so it depends on what we're rounding to. But so there's my answer in well, I guess I'm rounding to the year, right? Because I want to know what year. So in the year 2112, the amount of carbon dioxide will double from the year 2000. Okay. Another way you could do it is you could start estimating and do from back here. Well, from right here, you can start plugging in x's, plugging in years, and start and kind of guess what that might be, since you didn't know that this was the ln button. Yeah, so log with base e is the ln button. But you could start throwing in years and see what you get. You could look at the table, and you could say, okay, doubles is 7050, right? So somewhere it's between here, so you can start estimating somewhere in between here. Oh, that should be a 2, sorry. That should be a 2. So you could start estimating somewhere between this 100 years, right? It's going to happen somewhere in between there, so maybe about half, so you can start estimating there and start plugging in x. You could start plugging in x right down here into this equation and see what gets you closer and closer to that number. Okay, so I'm going to do the homework. I'll put that up on another video, but this is the end of section 4.2.